Hello, everyone. For those of you that don't know me, I'm Marcus Noble. I'm a platform engineer that works at Giant Swarm, and I won't talk much about that, seeing as Joe covered it this morning in the first talk. But I work on, mainly these days, around release engineering, CI/CD, and some like general Kubernetes cross-provider stuff. I also recently started doing a monthly newsletter where I talk about all things cloud native and all the things that have happened in the past month. So if you're interested in that, do check it out. And as of now, I've got about 7 years experience working with Kubernetes in production. Started off as a full stack Node.js developer doing web apps, and I was responsible for trying out this new thing called Kubernetes for our team to see if it would work for our quite large e-commerce offering that we had in this big multinational company. Turned out to be pretty good, and I ended up running 3 clusters for our team, dev, staging, and production. Moved on in the same company to a more R&D role where I was doing best practices and like tooling and stuff for the entire multinational organization, so hundreds of different teams, and then moved on more into platform engineering, building out the stuff that we did at Giant Swarm, so some of the stuff that Joe talked about earlier this morning, and more recently around release engineering, CI/CD, testing, stuff like that. Now, I'm here to talk about pods and do a pod deep dive. Now, I've got a little bit of a confession to make to you all. When I submitted this talk, I wanted to tell you everything there is about pods. I got to 100 slides. It was an hour long when I did my first run through. So we're all here for 2 hours for the full thing. You're cool with that, yeah? So yeah, I can't do a pod deep dive into everything. Instead, what I'm going to talk about is the interesting bits, the things that I learned while doing this initial talk that took an hour and wasn't even everything, and the things that are just a bit weird, a bit strange, a bit stuff you might not know about when it comes to pods. So, without further ado, what is a pod? I'm sure if you've used Kubernetes, you've come across it at some point. But let's go for an official definition from the documentation. Pods are the smallest deployable unit of computing that you can create and manage in Kubernetes. What we mean by that, by the smallest deployable unit of computing, so this is something that runs our containers or our WASM or WebAssembly, whatever. It's generally seen as a wrapper around one or more containers or WASM functions, managed by the Kubernetes scheduler and assigned to nodes at runtime. Workloads within the pod, within a single pod, all share the same runtime context. So these are things like your Linux namespaces, the same local host, things like that. They are designed to be relatively ephemeral most of the time and disposable. So you will see them get deleted and new ones created. And for the most part, most of the pod spec is immutable. There's a few exceptions, so the image, the active deadlines, they can be changed at runtime, but everything else you will get an error from the Kubernetes API server. So, as I said, but there really are much more than that. Like, there's too much for us to cover. So I'm going to talk about some of the interesting, weird, or some of the surprising bits that I came across as part of this. And these are the kind of sections we're going to go through today. And I'm going to quite speed through this because it is still quite a long talk when I did this. So I hope you're all buckled in. So we're going to start off with containers. So I hope we all know about containers, seeing as we generally all work with Kubernetes. And we know that a pod is a wrapper around one or more containers, and so I'm not going to talk about your app containers in general. What I'm going to talk about first are these sidecar containers that were first introduced, that were enabled by default as of 1.29, so you can use them in the latest versions of Kubernetes. And what's weird about these is they are disguised, as I like to call them, as init containers. So the way you create a sidecar container is you define it as an init container, and you set this restart policy property to always. And that is the only value that can be on that property, is always. And this is not to be confused with restart policy at the pod level. Now, if you set restart policy always on your init container, it will start as your pod is launched right at the very beginning, along with all other init containers. But once your other init containers have completed, it will continue running, and it will continue running until after your app containers have finished, and then it will quite aggressively be terminated, much more so than your app containers. You will generally see much harsher sig terms followed by sigint in these sidecar containers, so don't rely on any shutdown logic, generally speaking. I personally hate this spec. The way that they've designed this and how confusing it is, I hate it. I'm sure there's reasons for it, but I just want to call it out that I'm not a fan. Now, ephemeral containers are very cool. These are designed for debugging and figuring out why are things broken. I use these a lot. These can't be defined on your manifest. So this ephemeral containers that you see here, this is a read-only property. You can't write this and do a kubectl apply. You have to do it through a special ephemeral containers handler using something like kubectl debug command that you see here at the top. One little caveat is they're not supported on static pods. So your API server, for example, you won't be able to use these. And you can target either the entire pod itself or specific containers within that pod using this target container name property. For the most part, they have the same spec as all other containers, except for they don't have support for things like ports, probes, resources, and life cycles, because they don't really make sense in this context. These ephemeral containers are really just a case of let's get an executable shell in this environment that we can play about with. And if you have one that's running, you can reattach to it at a later date using kubectl attach, so you can continue debugging in multiple sessions. Cool. Now, pause container. So these have been around since the very beginning of Kubernetes, I think from the very start, I'm not entirely sure. But what I found interesting about these is when I was actually trying to write this slide, the official documentation for Kubernetes, the only reference that I found for pause containers was on the documentation page about Windows containers and nowhere else. Very strange, because they are all used for everything. For those that don't know, every pod that is created in Kubernetes gets a pause container. It's this empty container that its sole job is basically to set up the environment that that pod's going to run in. Create some C groups, some reservations, it sets up the networking, that kind of thing. And it can be thought of as like a parent container for all the other containers that your pod's going to run. So even if your containers crash through bad code, environment issues, whatever, the pause container keeps running so that environment remains available for your containers to use again when they restart. You can't see these pause containers through the kubectl API, so if you do a get pod, you will not see these containers listed. But if you go onto the nodes itself and you, depending on your container runtime, use, for example, with containerd, if you use the CTR command, you can list out all of the containers running on that node, and you can like grep for pause containers. As you see here, we're using a Giant Swarm specific one in our environment. Cool. Containers are done. Let's have a look at images. I'm going to talk very quickly about these, but image pull policy, I'm sure you're all aware of this to one extent or another, but I just wanted to talk about the different defaults that are available with image pull policy, because they may not necessarily be totally clear. There are 3 values that you can have for your image pull policy on your container. If not present, always or never. If not present will go and fetch the image from the registry, the container registry, if it's not already available on the node. So it'll have a look first if it's already in the node cache, and if not, go and get it. This is the default if you specify your image tag as latest or omit it completely, which then defaults to latest. The value always will always go and fetch the image from the registry. This is the default if you use, sorry, I got the defaults the wrong way around. The first one is if you don't specify latest, if you use a name tag. Always is if you do specify latest or omit the tag. Now what's interesting about always is it doesn't actually always go and download the image. It always goes and checks if it needs to download the image. So what it actually does, it calls the registry and says, what are the layer shards for this image? And it will check if it has those same shards on disk. If it does, it just uses those, doesn't download them. So you're not actually, it's quite nice that it won't actually waste bandwidth and all that kind of thing if you do use always. And then the final one is never. This is like the kubelet's like, the image better be there because I ain't doing anything about it if it's not. This is if you're using a third-party thing that will make sure images are available. Maybe you're in an air-gapped environment where your images have to be preloaded onto every node that you deploy. They have to be there. You can set things to never, and it will never try and call out to the internet. Image tags. Using a SHA-based image tag is best practice. The reason for this is you can be certain that the image you're pulling down is exactly the image you pulled down the previous time. Whereas named tags, so things that are like either latest, which is generally seen as mutable, that will always change as the new things are available, but also things like your v1s, .2.3s or whatever can also be mutable if you decide to do so in that image. Now, a char will always be the same. Char is based on the content of that image. So best practice says, let's use a char so we are certain that what we're getting is not a virus, not malicious, not whatever. What's interesting is, when you do use a char, the tag is meaningless. It's completely ignored. This example here is not for 125.1. It's a completely different version, and it'll pull down that completely different version, the one that matches the char. I can change that 125.1 to anything, and it doesn't care. But it still needs to be there. So be careful if you've got things like Renovate or Dependabot or stuff that updates these things in your GitOps files, that it does update the char and not just the tag, because otherwise you're not updating anything. Great, runtime class. So let's get to some actual running pods in this case. I'm going to talk about the runtime class resource and how it works with pods. So what this allows is for your cluster, for a single cluster, to have different runtime environments that it can support. By default, it will use whatever container runtime is defined on the node that pod is running on. So this is your container D, this is your CRI-O, this is your Docker, whatever you have configured in your Kubernetes cluster by default. But if you want to use a different one that you have installed, you can specify this runtime class name that has to point to a runtime class resource within your cluster that defines the other runtime that you support. Now, for that to actually work, your node has to have that runtime installed. So it has to have that runtime handler installed on the node that your pod is going to run on. And to make sure that pods are only scheduled on ones that have that, you can use this scheduling node selector on the runtime class to say, here is a label selector where any nodes that have these labels will have this runtime installed, so only pods that use this runtime class will run on those nodes. Now, it's pretty rare, at least from my experience, that you will have multiple runtimes for your containers, so it's very rare that you'll see CRI-O and containerd. But where you will see this is with WASM. So the way that WASM generally works is for your containers in your cluster, you will probably run like containerd or whatever it is. And then for your WASM functions, you may use something like WASM Edge that you define as a secondary runtime class that you can then run your WASM functions in the same cluster as all your other containers. And this is how it works. Cool, static pods. So I mentioned these very briefly earlier when we were talking about ephemeral containers. But for those that aren't aware of what a static pod is, these are managed directly by the kubelet. These are managed directly by the kubelet, not by the API server. These are always bound to a single kubelet on a very specific node, and they are defined either through a directory of static YAML manifests or via a URL that points to a YAML manifest. Now, the example on the right here is an extremely cut down version of a kube scheduler static pod that is just a file on disk on the control plane node. Now, this becomes a static pod, and what the kubelet will do is it'll see this file and it will create this pod in our cluster, and it will also try and create what is called a mirror pod. A mirror pod is effectively a read-only view of a static pod in the Kubernetes API server, so that when you're doing kubectl get pods, you can see these static pods and you can view the information about it. You can get the status, you can get the detailed stuff, but it's read-only. You can't make any changes to those through the API server. It doesn't do anything. To make changes, it has to be wherever the source is. They all get a suffix of whatever node they are running on, because these are specific to a specific kubelet and a specific node. So this kube scheduler will get something along the lines of kube scheduler control plane 1, and then for however many nodes we have. Because these are run by the kubelet and not by the API server, they cannot reference any other resources within our cluster because they don't know about them. They only know about containers, basically. So you can't have config maps as volumes. You can't have volumes, really, because you can't reference a persistent volume, you can't reference a config map, no secrets, nothing like that. So these are generally quite specifically to just running containers. And the kubelet will watch these sources, so either the directory or the URL, and when new things are found or removed or whatever, it does kind of reconcile those in a similar-ish way to the Kubernetes API server does. Great. Let's talk about lifecycle hooks. I quite like these on our pods, on our containers rather. There are two lifecycle lifecycle hooks that we can use on our containers. These are guaranteed to run at least once, but may be triggered multiple times. So if you can, try and make sure that that's fine and doesn't cause problems. As I said, there are two possible hooks that we can use here. There's a post start, which will run after our container has started. But there's no guarantee here as to whether it comes before or after the container's own entry point has run. So try not to rely on whatever happens in your entry point if you can. It's also worth pointing out here that the container that this hook belongs to isn't considered running until this post-start hook has completed. So don't have anything that just waits forever or watches, because your container will never be considered ready. An example of this is, I've taken this from the Cilium chart from Bitnami, where if you're running Cilium in a ENI AWS cluster, it does some IP tables stuff at startup that it doesn't include in the actual upstream Cilium image. It kind of does this as a hook. You've also then got pre-stop, which runs immediately before the container is terminated. So generally speaking, your application will get the sigterm command. It will do its shutdown logic, and then your pre-stop will occur. This can be used for things like cleanup logic. So in this example, they use it as an uninstall for the CNI plugin. I've used it myself personally in my home lab to back up an SQLite database to a persistent volume on a NAS share that I have it's just in an empty dir at runtime and then just ship it off. There's three different mechanisms that you can use for these hooks. Generally speaking, at least from my experience, you'll see exec, which allows you to run a command within the container. You can also have HTTP get, which performs a HTTP get command against the container. I've seen this in situations where you've got a web application where you may have like a pre-cache endpoint. So you can have that call as part of your start hook to pre-populate a cache within that web server. And then if you enable the pod lifecycle sleep action feature gates, you can have this sleep, which just pauses it for a while. Conditions and readiness gates. So you've probably come across conditions multiple times when looking at Kubernetes resources. They all have them in some degree or another, or most have them. And these are on the status. And for pods, the kubelet manages 5, with one of them being beta, itself to tell you the current state of the pod. Now, the first one I've got here is pod schedule. This will be true as soon as the pod has been assigned a specific node to run on. So this is when the scheduler has determined which node is best for it and has updated the pod spec.node name property with that node. The beta feature here is this pod ready to start containers condition. This lets us know when the sandbox and the networking is ready in the pod. Sorry. Containers ready is when all of our containers are ready. Quite straightforward. Initialized is true after all of our init containers have finished running, but not our sidecar containers because of, yeah. And ready is when everything is green, we're good to go. That means our load balance, our services can start pointing traffic to it. We can start scheduling workloads and whatever. And generally speaking, like each of these, I've not got it on the example here, but each of these usually have a machine-readable reason property that you can use to figure out if something's broken or not, and then like a human-readable message to be like, yeah, help me debug this, what's going wrong. Now, the reason I wanted to talk about these is because I wanted to introduce you to readiness gates, which I hadn't come across before, and I quite rarely use, at least from what I was able to find out. They've been around for a while. And readiness gates allow you to implement your own status conditions and have them as one of the checks that the pods will use as part of their is it ready or not. These have to be implemented by some external application, so you'll have another controller running in your cluster more than likely that handles is the readiness gate done. The way it works is it adds in this readiness gates, which is an array, and then this condition type. It's just a value here. This is an example from the AWS load balancer, ingress controller, whatever. It adds that, and then it will update this condition down here that has the same type as the condition type. And in this example, what it does is once the ALB or NLB that is related to this service is ready and can start serving traffic to the pod, that will then update the status to be true, which, assuming everything else is true, we'll be able to set the pod's ready status to true as well. This means that until this external resource, this AWS ALB or NLB is available, we won't start serving traffic to this pod because we know it's not going to work properly because we rely on something external, and we can do this through readiness gates. Config. So config, when I was doing this original talk, huge topic. Config maps, volumes, all this kind of thing, loads to talk about. That's a whole 2 hours worth right there. So this is going to be very brief, or very picked little bits out that either bugged me or found weird or whatever. So we're going to talk about environment variables first. One thing that I had come across before but never really registered with me was you can actually have dynamic environment variables in your container spec. So you can reference other environment variables in your environment variables. So here, this would actually come out as greeting would be hello world, because we can reference these other ones through this parentheses syntax rather than the braces syntax that you normally have when referencing variables in Bash and things. Now, where that might be useful, rather than the hard-coded example I had previously, is if you use it with the downward API. I love the downward API. This allows us to expose properties from our pod and a few other things as environment variables into our containers. You can't expose all properties. There is a subset of things you can, but you can expose things like some metadata from the pod's metadata, so the name, the namespace, the labels, annotations, things like that. You can expose some of the spec. So one of the things that you probably see in a fair few examples is the node name. So this gets added by the scheduler to the pod's spec.node name. This allows your container to then have an environment variable that says what node you are running on. You may need this for handshake logic with other pods in a replica set or something. Quite a lot of the status properties can be exposed. So the pod IP is often one that you will see here, so that the thing that your application knows what what IP it has to the outside cluster. And then you can also expose limits. So limits being your resource limits, so your CPU and your memory. This is very useful if you have applications where they need to know how much memory they are allowed to use without causing OOMs. So if you can tell your application, don't use more than what my limit is, it will hopefully not get to the OOM stage and kill your container. Now this, I hope you can kind of see where this dynamic environment variable might be useful, that you can then reference these other environment variables to build up more complex ones, perhaps. Cool. Volumes. Again, volumes, huge topic. Huge topic, but we're going to talk about a few things. This annoys me. When you're referencing config maps versus secrets as volumes, config map is configmap.name, secret is secret.secretName, and I hate this inconsistency so much. I know it's never going to get fixed, but we need a V2 just to fix this. It bugs me. I have to look it up every single time. Again, we can use the downward API with volumes, so it doesn't have to just be environment variables that we use all these nice pods information. We can actually create files on disk, or in our pod, on a container, whatever. So for example, we can have the labels and the annotations created as files in our pod. So here, the path becomes the file name, and it's mounted into etc/podinfo/labels/annotations. Empty DIRs. I'm pretty sure a lot of you will have used these to some degree or another, but generally speaking, you will see this as just curly braces, empty, no values set. What you may not know is it has a medium property. You can tell it what medium to use for the empty dir. By default, generally speaking, this is disk from the node that the pod is running on. So sort of like host path volumes, but not quite, a special directory, that sort of thing. You can specify memory, which creates an in-memory empty dir, an in-memory file system. So this is good if you need something that's very fast, writes to memory, reads out, all this kind of thing. Just be very aware that this will then take memory away from other workloads on that node. So maybe not the best, but if you do need something very fast, great. Size limit is a best practice to use, in my opinion. This allows you to specify the amount of disk space that this empty dir is allowed to have. This prevents you from utilizing or exhausting resources that other applications on the same node may need and break if they run out of. This works in a couple different ways depending on the medium. If it's if it's using the default, you will get, the pod will be evicted if it goes over this and get rescheduled. If the medium is memory, it actually just reports it back as no space left on device. So it's a bit inconsistent there, which is not great, but yeah. And then finally, not finally, we also have projected. Hadn't come across this one too much, but this allows you to kind of merge multiple volume sources together into a single volume mount. It doesn't support everything, so it supports secrets, config maps, download API, service account token, and cluster trust bundle. But for example, if you have a config map and a secret that has all your apps information in, you can use a projected volume type to then mount that as a single file in your application or whatever, or single mount point. And then one thing that I want to talk about that's still alpha as of 131 and therefore disabled by default is the ability to use OCI images as volume sources. So this is very cool and allows you to have things like, I've seen examples of machine learning models as OCI objects that then get mounted as directories within your pod through this kind of interface. And it's a similar sort of thing as with containers, same image pool policies, all this kind of thing. Scheduling, resource allocation. So I talked about this briefly. I'm not going to go into details about this. There is much more knowledgeable people that can talk to you about this. The reason I wanted to talk about resource requests and limits is because I didn't realize that you could have more than just CPU and memory. It's possible to define GPU, for example. So the NVIDIA GPU driver has this nvidia.com/GPU resource request and limit that you can define that tells you how much of a GPU your application wants to use. And you can have multiple of these, like AMD GPUs have the same or similar. And there's a few caveats here. So for the this GPU one, for example, they have to be the same. You have to specify limits. You can't specify, yeah, it's weird. But it's some limitations of the implementation. But like, you can have your own custom resources, which is pretty cool. And a KEP that's currently in progress is the pod level resources that allow you to have the same sort of thing, but rather than having all of the container level resources added together and exposed as the pod level, you can just define a single time for the whole pod and allows you to more easily say this entire pod can't use more than a gig or whatever. Node assignment. So the only thing I want to talk about here is, because it's the only thing that was new to me and I hadn't really come across before, is topology spread constraint. Now, I haven't got much time left, so I'm going to be very quick about this, unfortunately. So please look it up elsewhere if you're interested. But this allows you to have more control over where your pods end up getting spread to. It has this concept of a skew, which is the number of pods within a given topology minus the minimum number of pods within any topology. Now, a topology is a grouping of nodes with a given label. So in the example I've got down here, we're using a zone label. So we've got zone 1 on the left, zone 2 on the right. And with our example, because our skew is 1, even though both of them match our pod's label selectors and all this kind of thing, it will attempt to put it into zone 2 because that gives us the least skew from what we want. It more evenly distributes them across. What's worth being aware of here is this is not guaranteed to be honored when scaling things down. So if you've got a horizontal pod order scaler, when it scales down, you may end up with skew because of this. But when things get rescheduled, you should try and do it. Very quickly, I'm going to talk about priority and preemption. This allows you to say this pod is much more important than this pod. You can define this pod priority, this priority class, that you then associate with your pod. It's just a number the bigger the number, the more important it is. And there's a few things you can do with this. Depending on whether you set the preemption policy to never or not on your priority class, if it's set to never, you won't evict other pods if a higher priority one comes along. If it's not set to never, then if a high priority pod needs to be scheduled and there are lower priority pods elsewhere, it will kick them off and get that scheduled. Otherwise, it's just a queuing thing. And I am very quickly running out of time. This is all I just want to say. You can have multiple schedulers, which is pretty cool. You can define a scheduler name on your pod spec and tell it which scheduler to use for your pod. So if you have something that's like super specific, super bespoke in your environment, you can have that handle it instead and decide where to go. Yeah. Networking, everybody's favorite thing, and obviously I can get through this very quickly. DNS, yeah, I'm going to skip over a bunch of this, but every pod gets a host name. The host name is generally the name of the pod, but that can be overridden either with the host name or the subdomain property. You can add some more host aliases and things like that. What I do want to talk about is the DNS policy, where the options are default, cluster first with hostnet, or none. The default is not default. The default is cluster first. There are reasons for this, but naming is hard, all this kind of thing. Default is actually the default from the node that you're running on. Whatever the node's DNS configuration is, that's the default. Generally speaking, you want cluster first, because that allows you to resolve things within the cluster. If you've got host network, you can use host with it, yeah. If you set it to none, then you have to tell it everything. So you have a DNS config, you have to define everything, and it creates basically a resolve.conf within your container, and you have to define where all your name servers are and things like that. So to wrap up, I hope this is better than the hour-long talk that I was originally going to give. And I hope there's at least still interesting things in here. I've been quite worried about this, that I wasn't able to actually include all the things that I wanted to because of there's a lot to cover. So hopefully at least some of this is still interesting and things like that. And I would very much appreciate feedback on this because it's the first time I've done this talk. It's a bit different for me. So good feedback, bad feedback. Found it useful, found it terrible, whatever, I would love to hear it. Reach out to me, come find me. Thank you very much.
We made it to the end of the day. Any questions? We've got time.
Do we?
Well, there's no more talks.
Cool, we got 2 hours worth of questions. Let's go. Can I grab my drink first?
Thank you. Could you please go back to the slide with the host name and the subdomain name?
Yeah.
Okay.
I know everybody loves DNS.
Yeah, that one. But that one, most probably, doesn't create a DNS record, does it?
No. Yeah, I wish I had more time to talk about it. Yes, this is inside the pod itself. So this is the host name that the containers themselves see, not what other pods see. That's core DNS or whatever is responsible for that. So even if you set host name to my super cool host name, other pods within your cluster will still see it via the name of the pod because core DNS is responsible for that. Yeah, I hate that as well. I don't understand it. If somebody can explain to me why that is good, great, I'd love to hear. Anything else?
Anyone else? No? Awesome.
Cool. Thank you very much.
Thanks very much.